Right. So as Amy said, I'm Charlotte Tomlin, and I am a preventive conservator with Spencer and Fry. And today, I know you're all very excited. I'm going to talk to you about environmental monitoring and control in a museum environment. Apologies, because this is virtual training. It's going to be a bit PowerPoint heavy. But if you do have any questions at any point, please do write them in the chat. And then periodically in between my sections, I've got a little section for questions, which I'll just have a look at the chat and see what questions there are and answer any you might got. If you want to leave it to the end, then hopefully we'll have a bit of time at the end to answer more questions. And hopefully, if it works and you're all interested, there is a little bit of an engagement activity at the end, which you may or may not find very exciting, but as I am a preventive conservator, I do quite like looking at things like temperature and RH graphs. So we'll see how we get on there. But first things first, we'll just go through a little PowerPoint all about environmental monitoring control. So here we go. So yeah, this is the schedule for the training. We've done our introductions. I hope you're all feeling very welcome. I'm just going to go do a bit of a recap on the agents of decay. Not going to go into it too much because we're going to focus on incorrect temperature and relative humidity today and light, and go on to talk about how we can monitor and how we can control these agents of decay. Apologies for anyone who has quite a bit of knowledge on conservation matters, because I have started quite basic for anyone who is just developing their knowledge of museums and conservation. So hopefully there'll be a bit for everyone, but apologies if there are some things that you know, but I always find it's good to have a refresher, even if you do know these things. So hopefully you enjoy. So agents of decay, what do we mean by that? In a museum setting, this is what we call anything that can cause damage or deterioration to museum objects or museum buildings. And I've done a really pretty, I think you'll agree, little decorative word image there for you, just to list all of the agents of decay, depending on which source you look at. There's about 10 or 11 main agents of decay, including ones you can pick out here. So we're going to talk about incorrect temperature and relative humidity and light, but there's also things like dust, pests, fire, water, vandalism, theft, pollutants, disassociation. You might not, well, I think pretty much most of them are pretty obvious. Dissociation is where an object loses its identity because of loss of information. So you don't know why something is important or why you've got it, which can be an kind of not thought about deterioration value of an object. But I think most of the others are pretty self-explanatory. So that's what we focus on in preventive conservation, and what we try to reduce the risk of, so that objects that are important to us can live as long as possible and be displayed, studied by many people for years to come. So that's all I'm going to say about that, because we're going to focus on three agents of decay today. The first we're going to lump together two, so incorrect temperature and relative humidity. These are very big, important factors in a museum environment, and we'll see why now. So I think most people, I think everyone here, we understand temperature. Cold, hot, don't really need any more explanation about what that variable is. However, relative humidity, if you've not come across it before, generally shortened to RH, and I will probably revert back to calling it RH throughout the presentation, so apologies, but you've been warned. It means relative humidity, and it's how humid the environment is. It's how we measure and how we refer to how much water vapor is in the air. So RH in particular, I've put this little equation on because it's the easiest way to explain it. Don't worry too much about it, but it's the amount of water vapor in the air divided by the total amount of water vapor that air can hold at a given temperature, times by 100 because it's a percentage. So if I have a given temperature of, so say it's 20 degrees, and at 20 degrees, the air can hold this. I don't know whether you can see me amongst the PowerPoint, but hopefully you can see me because I'm waving my arms around. It's holding. It has a maximum amount it can hold at that temperature, but at the moment it has 50% of that amount. So that we would call that 50% RH because it's equation. But like I say, don't get too bogged down in the maths. Basically it's a scale from 0 to 100%, and depending if it's 0, it's very, very dry. It's 100, it's very, very damp. And we will now go on to talking about why that's important and what that can affect in the museum environment. And you can see here, so everything's at a given temperature. So temperature can affect the RH percentage. And that's why we think that temperature is quite important in this context. But I will stop talking because I'm confusing myself there. All you need to know is the percentage from 0 to 100, dry to wet. And I'll talk about incorrect levels in a minute. But what type of damage can incorrect relative humidity and temperature cause? And what levels are we aiming for to prevent damage from happening? So temperature and relative humidity can cause the following types of damage. So mechanical, chemical, biological. And I'll just chat about each individual one just to give you an idea of what kinds of damage I mean by this. So mechanical damage, so anything physical happening to the object. So for example, objects made of different materials, inorganic, such as metal and stone, organic, such as wood, paper, they respond to temperature changes. So they can expand when they get hot and contract when they get cold. But pretty much it's extremes of temperature you need to worry about that. And we'll have a look at some pictures of what materials expanding and contracting can mean. And mechanically as well, organic materials, so ones that are natural fibers, things like wood, wool, leather, they are hygroscopic, so they contain water as part of their internal construction, and their internal moisture content can be directly affected by the water vapor in the air. So they can respond to changes in RH. So for example, if the RH is very dry, so in the lower percentages, the materials can give out water and start to contract. If the RH in the environment is very high, so high percentages, damp, materials can take on water and expand. So it's quite similar to high and low temperatures, expanding and contracting. And why does this cause damage? Well, if you've got an object of one material, it possibly won't, unless it's very extreme. However, objects are normally made of many different types of materials, and they all react slightly differently to these expanding and contracting under temperature and relative humidity. So when you've got a composite object, whether it's made of different metals, different woods, a combination of many different types of materials, or even just one or two, as they are expanding and contracting differently, they are building up pressure between the materials, and that's when damage is caused. So we'll see some pictures in a minute about what I mean about mechanical damage. chemical damage. So things like chemical reactions occurring within the object and causing degradation. And the key reactions, don't worry too much about this, but the key reactions we are talking about are things like hydrolysis and oxidation. So reactions that occur between a substance and water and between a substance and oxygen. And these are the main deterioration mechanisms that cause decay of many objects. So, for example, changes in temperature can affect how quickly these chemical reactions that cause degradation happen. So heat speeds up any chemical reaction. The rule of thumb is that the rate of reaction approximately doubles for every 5-degree increase in temperature. So all these natural deterioration mechanisms that are happening can increase as temperature increases, so lifespans reduce. And again, relative humidity is significant because moisture, I mentioned hydrolysis reactions. They're reactions that can only take place when water's present. So if you have a high RH, a damp environment, that will cause more reactions to take place and further degradation to happen. And again, I know you're really looking forward to the images that I'm going to show you that will make sense of all this. And then lastly, biological damage. Very simply, organisms that cause damage to materials such as mold and pests can be encouraged by high RH damp environments. And again, I've got some lovely photos to show you. So that's all the sort of chemistry, well, not all the chemistry, but hopefully most of it. And we'll have a look at some photos of what I mean. So I said about materials expanding and contracting. So here we can see a table, a folding leaf table, and you can see the top leaf there that's folded over has changed shape. It's warped out of place, and that's what I mean when things are expanding and contracting in response to RH. So this table is expanded and warped out of shape, and it's now permanently deformed. So warping can happen, cracking can also happen as materials pull apart. And like I was saying, when with mixed media objects, particularly where organic and inorganic materials, so organic as in the natural fibres and inorganic such as non-natural fibres such as metal, stone, when they're together, they react hugely differently. So an organic material will expand and contract more. Well, it will expand and contract in reaction to RH, as we said before, whereas metal won't. So this piano, this harpsichord, the wood has expanded. You can see in this second image here, the top has warped out of shape, and you can see here that the little metal clasp has broken in reaction to that pressure, because it hasn't expanded in the same way. So the neighbouring materials can cause quite a lot of damage to each other as they react to this changing environment. But it's not just different, it's not just between inorganic and organic. Organic materials, although they do react to RH, expanding and contracting, they don't react the same. So for example, this painting surface is made up of a substrate, maybe canvas or wood, and then there's many different layers of paint and varnish on top, and all of them layers are expanding and contracting at a different rate in relationship to the relative humidity levels in the air, and you get this crizzling craquelure effect that you quite often see on old oil paintings that have damaged the surface, and that's RH is a big contributor to that. And again, this table leg, it's got a wood substrate with a veneer wood, very thin veneer wood, decorative wood on top. And because they are different thicknesses, they're different woods, they have expanded and contracted in different ways, and they've pulled apart, and the veneer has flaked off the leg, so causing obviously quite a lot of damage there. And you'll notice that I'm mentioning RH a lot, mainly because RH does have a bigger effect than temperature. I've said that temperature has an effect on the RH, so temperature is important because it controls the RH. And obviously extremes of temperatures, as I've said, are not good. And the hotter the temperature, the quicker reactions happen. However, it is RH that we do tend to worry about more, because it does more often than not cause this contracting and expanding that we worry about. However, temperature is important as well, particularly high temperatures, because it can cause things like adhesives to soften and break apart. So if an object has been mended, or even if it's in its natural form, adhesives are used to create objects. If it gets very hot, the adhesive can soften and things can start to break apart. As you can see here, this repair has fallen apart where the adhesives failed, and you can preempt here, this foot of a table has been repaired previously with adhesive, so if temperatures get very hot, that will maybe start to become unstable. High temperature can also cause coatings to become tacky. So if there's a wax coating on anything, you might start to feel the surface becoming sticky. So whilst I haven't mentioned temperature as much, it does have an effect, but we do worry about RH a lot more in the museum environment, and I think that confuses people slightly, because in our normal homes we worry about temperature because we want to be warm enough, but in the most part, collections are more susceptible to damage by RH changes. Yeah, so another mechanical damage with fluctuating relative humidity can be an inherent issue as well. So for example, in contexts where salts might be present, so if you've got a collection that has been recovered from a maritime context, or if you have a building that suffers from groundwater damp, the salts from the groundwater or the salts from the marine environment, as RH circulates and becomes damp and dry, these salts can I can never say this word, effervesce. You know what I'm trying to say. They can appear as the environment gets dry, they crystallize on the surface. So we can see here, this wall has obviously been damp with groundwater. The groundwater contains salts from the ground, and as it's dried, the salts have crystallized on the surface there. And as the salts crystallize and reabsorb and crystallize and reabsorb with circulating RH, damp, dry, they can cause physical damage and cause eventually the tiles might be pushed off the wall. And this cork, this bottle recovered from a maritime context, so salty seawater, it's been impregnated into the cork. And as the RH has dried, the salts have crystallized on the surface. And again, if they continue to be reabsorbed and crystallize, they can cause the breakup of the cork, because the salts can create pressure and force the material apart. So it's important, particularly if you have a maritime context or a building, to be aware of salts appearing and what problems they can cause. So on to chemical damage, reaction and chemical damage, the most obvious being corrosion of metals. So oxygen and high RH, damp, relative humidity conditions can catalyze the corrosion of metals. So we obviously call iron corrosion rust. We're used to seeing that in many contexts, but in museum environments, not good, because it means that the stability of your object is reducing and deteriorating. Surface details can be lost, structural integrity can be lost, and some metals are more susceptible than others. So iron is very readily corrodable in damp conditions. Other materials such as gold and silver are more inert, and they're called noble metals. However, they are normally alloyed with a less noble metal, so they are still susceptible to corrosion. So for metals, particularly from archaeological contexts, they are particularly unstable. They have been manufactured from an ore, a natural state, forced into a metallic state, and they're consistently trying to get back to that natural ore state, particularly archaeological metals that have been buried and have been undergone more deterioration over time. If you've got them in your museum collections, they are more readily susceptible to corrosion, even in quite low relative humidities, in like quite dry environments. And they need very dry environments to prevent corrosion from reoccurring. And the other thing to be aware of with corrosion is, yes, it does only affect metals, but if you've got a composite object that has a metal component that's corroding, it can stain other materials. It can, as corrosion causes expansion of metals, so if it's a quite tightly bound object, it can cause damage, like we saw with different materials, with the keyboard instrument and the metal hook. If the corroded metal expands, it can put pressure on other materials, neighbouring materials, and cause damage. So it's just being aware of the knock-on effects. So yes, corrosion's the main issue, but it can cause other issues. And related to corrosion very closely is tarnishing of metals. So this is very much a similar process, but happens to the more noble metals such as silver and things like copper. The surface can become tarnished, polluted by a chemical deterioration, so silver can turn yellow and then black. And these reactions, again, are catalyzed by damp environments and high temperatures, although specific pollutants are also necessary for this to occur. So it's not just a reaction to damp environments. And chemical damage of vulnerable materials as well. So as I've said, all of our materials are decaying. We are just slowing down the processes. But some materials want to decay faster than others, and this includes things like rubber and paper. Because these have inherent deterioration, they have acidic compounds. For example, paper made of wood pulp have acidic compounds that are continually trying to degrade, and things like high temperatures and high RH levels, damp environments, can speed up these mechanisms. So although they're not the cause, they do help to speed things up. So controlling incorrect temperature and relative humidity can slow these mechanisms down, although they can't stop them completely. So I've said rubber, paper, things like plastics and photographs as well. So things with inherent deterioration, inherent instabilities, but mechanisms that are sped up by what we're talking about here, relative humidity and temperature. And lastly, onto biological damage, which brings me to this lovely photo, and it's a good job we're not too near lunch at the moment. So mold growth can grow in conditions anything over 65% RH, so in damp conditions. It can't grow in dry conditions. So mold is not good for objects. It can cause staining, and the mold gradually eats away at the material it's growing on. And the issue with mold is that mold spores are everywhere. You can't eradicate them completely. So as soon as RH goes above the 65% level to a damp environment, it can start to grow very quickly. And here, I love these photos, a bit sad, but so this is in the tunnels at Dover Castle, and which is a very closely controlled environment because it is very susceptible to mold. And the control system broke. So very quickly afterwards, about 24 hours afterwards, this mold growth was found. And what's really interesting about this mold growth is that it's concentrated in the second photo. You can see a very concentrated mold growth there compared to the rest of the area. And that's where the operator would have put their hand. So their hand would have been their operating thing, the equipment. So you can see the mold growth is showing you historic use of the object, because that's where the organic material from the person's hand has accumulated, and that's what the mold is feeding off. So whilst mold is not good, it's quite interesting in this context because you can see historic use. But mold does just, as I said, just grow on organic objects. So things like wood, leather, anything plant, animal based. However, it will grow on the surface of inorganic materials if there are organic contaminants, as in this case, such as the organic skin cells and things from this person's hand. So whilst you need to be aware of it primarily in response to organic materials, it's also worth looking at inorganic materials if you think they might have food or skin cell residue on there, because mold can attach to the smallest little particle. And the other thing to be aware of with mold is that it is a bad health risk for us. So if you do come across mold in your museum, it's important to think of your own health and use correct PPE. So FFP3 face masks, gloves, and possibly overalls as well, and seek, if you do have a massive outbreak, to seek professional advice before risking your own health. And the other biological damage that we're worried about is pests. And pests really like quite damp, humid environments. So whilst they are an agent of decay in their own right, they are encouraged by high temperatures and high RH damp conditions. You can see this lovely photo of a wicker basket with quite severe furniture beetle infestation. So the image on the left showing the holes, if you can spot them, and little piles of frass on the table, and then a really lovely close-up of a larvae in action, which is why it's not good. It's good that we're not close to lunchtime. But obviously pests attacking materials undermine the structural integrity of the object and can cause quite severe deterioration. So we've talked about what can happen in incorrect RH and temperature, but I've not really said, apart from things like damp and high temperatures, I've not really specifically said what is the correct temperature in RH, and that's because it's a bit of a movable ship really, depending on the material. But in general, so you can see on your screens, these are the general things we say in a museum environment, because we are aware that most museums have a mixed collection. So you can't create an environment that's specific for one material, really, if you've got a mixed collection. So in general, we say keep your temperature between 5 degrees and 22 degrees. Obviously, if you have people working in the space, or if it's a museum that people, the actual display areas, we tend to say 16 degrees for human comfort. However, for storage and things like that, objects, as long as it's not freezing, objects don't really mind lower temperatures. I'm generalizing, of course, there are always things that don't, but in general, we say above freezing and below very hot temperatures, where things can start to become tacky, although obviously it's difficult on a day like this. RH, for a mixed collection, we generally say between 40% and 65%. 65% is the mold threshold, so you don't want to be going above that. 40%, any lower and you're getting into quite dry territories that some objects love, but most start to dry out and crack. So that's what we say for a general museum collection. And the important thing is fluctuations. So things can go a bit above, a bit below. However, if your environment is changing quite dramatically, quite quickly, that's when we start to see a speed up of things expanding, contracting, and salts crystallizing and dissolving and causing more damage. So we tend to say less than plus or minus 10% in 24 hours. But caveat, lots of material types, particularly vulnerable material types, love specific conditions. And whilst you shouldn't control your whole museum to cater for these vulnerable material types, you can sometimes create microclimates, so small enclosures that can be controlled further. So inside of boxes or rooms. So vulnerable material types such as archaeological metals, I mentioned, like really dry environments to prevent corrosion. Photographs and plastics, because they are particularly inherently vulnerable to deterioration. They prefer lower temperatures to slow them decay mechanisms down. But we'll talk about more about that under control. Right, so a bit of a break from RH and temperature for a bit. Hopefully you're still with me and you're not asleep quite yet. Light. So back to a bit of chemistry. The spectrum of light is quite complex, and I am not a scientist. However, generalization, this is what it's divided into, and what we are particularly worried about is ultraviolet and visible light. You can see they're sort of mid-range of the table. Light is a form of energy, and it's expressed in wavelengths, and the general rule is the shorter the wavelength, the more energy it has and the more damaging it is. We would be very worried about X-rays and gamma rays. However, in a museum context, luckily we don't often come into contact with them because they are very damaging to us as well. But ultraviolet and visible light are very much within our museum context, and we worry about them. So nearly all light sources contain a mixture of UV, visible light, and infrared, but the type of light source dictates the amounts of these. So by light source, I mean natural light, an artificial light, and different artificial lights such as LEDs, halogen, tungsten, emit different makeups of these three lights. And very simply, light causes chemical damage to objects. Because it's a form of energy, the energy excites the particles and the makeup of the object and causes reactions to happen, which occur even at low light levels. And the important thing to know about light damage is that it's cumulative and it's irreversible. So once it's happened, we can't bring it back. Organic components are particularly susceptible. So like I said, natural materials such as wood, paper, textiles, well, natural textiles. And the only things that are immune to light damage are stone, metal, ceramics, and glass. However, these for materials may have components, coatings, decoration that are affected by light, so don't rule them out completely. So pictures. One of the major deterioration caused by light is colour change, and I think we've all noticed that this in our day-to-day life. If you put photographs in the window, near the window, or textiles near the window, they tend to change colour. You can see in this image a tapestry, and for many years the bottom of the tapestry, you can see a line near the top. The bottom of the tapestry was folded up and wasn't on display. You can see that the bottom of the tapestry is much brighter colours than the bit above, which is much more faded and dark. So yeah, colour change and fading is caused by exposure to light. And in particular, some pigments are more susceptible to light damage than others. So for instance, organic pigments, which tend to be like yellows, tend to fade more quickly than other dyes. So for example, you can see here, the faded one on the right looks very blue. So the greens have faded to blue because the blue dye is more light fast than the yellow that make up that green. So you don't get a balanced fading of all the colours. You start to see a distorted image that's very different to the original one. It's not just that all the colours are faded, colours start to change. You can see many blue trees as you if you frequent many historic houses with tapestries. Many of the tapestries have blue trees and blue grass, and that is not how they would have originally looked. But it's not just dyes and textiles. Wood can fade as well. You can see this piano, which the keyboard lid has been kept up for a significant period of time, and you can see the wood that would have been protected with the piano lid up is much more vibrant and slightly darker and shiny, whereas the wood, particularly where the keyhole is, which would have been exposed to light much more often, is very dull and faded. But as well as colour change, structural damage can also happen, particularly to vulnerable materials such as silk. So this is generally higher energy, shorter wavelength light, such as UV light, that can cause so much damage that the object starts to fall apart. So for example, this silk scarf with quite a few holes in it, and on the right, 2 slippers, one which has been protected from light and one which has completely degraded in light. And again, some more images of structural damage. So a fire screen with a silk back, again, has become completely deteriorated. And obviously curtains in particular, because they get the full brunt of light at the window, you can often see them starting to fall apart if you visit a lot of historic houses like I do. So what are correct light levels? Again, it's a guide, because as I've said, there is no, unless you exclude light completely, you do not stop the deterioration. But what scientists and museum experts have come up with is that these levels present an acceptable amount of deterioration that will extend the life of a vulnerable object, but it won't completely save it. So for things that are very light sensitive materials below 50 lux, so very light sensitive materials include costumes, textiles, fur, feathers, dyed leathers, prints, drawings, watercolours, manuscripts, photographs, lots of things. And then below 200 lux for light sensitive materials. So these things are more light fast but still vulnerable, such as oil paintings, lacquerware, plastics, wood, horn, bone, ivory, undyed leather, and more modern photographs. Eliminate all UV. So I didn't go into detail earlier, but obviously UV is the thing that contributes to sunburn for us, so we protect against it. UV is not needed to see by, so it's what we call the visible light is the light that we need to see museum objects. We can't exclude that completely. UV is not needed to see an object. We don't need it, and it causes, because it's shorter wavelength, it's higher energy, it causes much more damage. So we need to eliminate it as far as possible. And we'll go into how to do that later. And then what's important with light, because it's cumulative, yes, we say 50 lux for very light sensitive materials. However, it can be a reciprocal arrangement in the fact that if your 50 lux is kind of the level they came up with, if you're a museum that's open every day for objects that are in the light every day, if you're not a museum that isn't open every day, you might want to look at max annual exposures as well, because these are the annual exposures that are deemed acceptable to create acceptable deterioration, which are based on the 50 lux and the 200 lux levels. But if you're not open every day, then you might be able to have slightly higher lux if it's an issue. But in general, 100,000 lux hours for very sensitive materials, 450,000 lux hours for light sensitive materials. So lux hours are very simply the lux level, which is how we measure visible light, times by the amount of hours that it's exposed to that light. And I'll talk about how we control exposure, max annual exposure levels as well a bit later on. So I haven't, let's see whether I can, oh no. I'm not sure I can actually see the question tab when I'm sharing screen. So I might just continue and do questions at the end if that's all right. But please do, as a question appears to you, put it in the chat, because I don't I don't want to interrupt the flow, but yeah, I think we'll do questions at the end if that's okay, because I can't see the chat at the same time as sharing my screen. So on to monitoring. We know what deterioration it can cause, a bit about the science behind it. How do we monitor temperature and relative humidity so we know whether it's unacceptable or not? So very simply, a basic, simplest of indicators is this RH strip. It's not precise, but it gives the RH to the nearest 10%. So the colour change, the strip colour changes depending on the dampness, and the colour change you read the RH where the colour change is. So for this one, it starts to change colour between 40 and 50% from pink to blue. So the RH is between 40 and 50%. These are pretty affordable, and they give you a general indicator of what the climate is like. They're generally not used to monitor the whole museum environment, because they are just a very general snapshot, not precise, and they can't give continuous readings. However, they are used a lot to monitor microclimates that I mentioned earlier. So things like if you've got a box of archaeological materials, that that are being controlled in a low RH environment. If you pop one of these slips in, you can see it through the box, and you know when to change out them controlling materials when that environment becomes unacceptable. So they are useful, but generally used specifically for microclimates, or if you have a display case that you'd like a bit of an indicator in. So next is monitors that you can take, handheld monitors that you can take spot checks with. So I've got one of these, which is called an LSEC, and I take it around to museums with me to take spot checks of temperature and RH. So it does a good job. You can tell what the RH and temperature levels are. However, regular spot checks have to be undertaken. It is only a spot check of that particular environment at that time you take the check. And if you're wanting to monitor the environment continuously, you have to do regular spot checks in the same place, the same time every week or every day. And you can then build up a basic overview of seasonal condition changes and what your environment is like. But that takes quite a lot of staff time and to do that, to do the spot checks, to record it, to look at it. And you won't have a full environmental picture because you won't know what the conditions are at other times, particularly at night, because I've not met anyone yet who thinks, yeah, I'm really dedicated to the museum life, I'll take spot checks at midnight and 1 a.m. With my spot check LSEC. But it is very useful to start to see the conditions, or for supplementing other methods. So what's the next step up? So data loggers. A lot of you will be familiar with data loggers. They are very useful. They take continuous, you can set them up to take continuous readings at a set time, and you can download them to get the data to see what is happening in your environment. So they provide a much more comprehensive picture of your museum environment, that you can start to really understand the conditions. However, the main drawback with this is that you can't see data as it happens. You can't see the current conditions. Well, you can't see the current conditions for the one on the right because it doesn't have a display. You can see the current conditions on the one on the left because it does have a display. However, you can't see whether it's heading up or heading down, or the past hour. You have to manually download the data before you can look at the comprehensive view. So reactions might be a bit delayed if you notice a problem. And these are basically the more up-to-date version of the old thermohygrographs, which did do continuous monitoring, but did it with a pencil on a little roll of paper, but same kind of idea. And the next step up, which is probably the most effective monitoring systems, are the telemetric or Wi-Fi Bluetooth systems. And these provide the same as data loggers, but with the bonus of being able to access live data. So the data is transmitted instantaneously to computer software, where it can be accessed and viewed live. It doesn't need to be downloaded, so there's less effort in collecting them, downloading the information, and then a delay in reaction. You can react then and there if you're looking at the data regularly. So telemetric systems such as Hanwell on the left, they tend to have to be installed professionally and attached to a computer system. And there are generally costs with data hosting and things like that. However, as technology continues to develop. We've got more and more of these Wi-Fi Bluetooth systems, which are much more easy to install. However, they still do have the costs of, you might have to subscribe to the data platform. And it is also worth bearing in mind that as this technology becomes more accessible and cheaper, there are a lot of things on the market that might not be as reliable and accurate as the original systems developed for museums and food industry, that needed so heritage industry and the food industry need particularly the food industry need the accuracy and the reliability of the data, whereas there's a lot of things on the market now that they might be reliable and accurate when you buy them, but they become less so much more quickly. So just beware, whilst there are a lot of cheap systems out there, they may not be fit for purpose. But there are a lot of very interesting systems such as Conserve and Testo, I think that's Testo, that are becoming more affordable and provide accurate data that you can access from your phone whenever you want. So if you've not looked at RHT, relative humidity and temperature data before, this is what it kind of looks like. So this is data from a year, so it looks a bit like, oh, what's going on? Normally we look at it a bit more in detail, and we'll come on to that later on with the sort of activity later on if you're feeling up to it. So that's the kind of thing that the continuous monitoring gives you, such as tiny tags, the telemetric and Wi-Fi systems, data loggers and telemetric systems will give you. So you can see it's a much more comprehensive idea of what is happening in your environment 24 hours a day, 365 days a year. So looking at that, it provides much more data to be able to see what kind of control you might need in your museum. So monitoring lights, very similar to monitoring RH and temperature. Again, there's the more generalized snapshot here. We've got blue wool standards. So blue wool standards are bits of wool dyed blue, and the dye fades at a known rate. So you can put, you might have noticed them in National Trust houses if you frequent them a lot. These generally popped next to light sensitive objects, and then you can compare the amount of fading to a set standard to see what the light levels are and how quickly something might fade. So that's sort of like the reciprocal to the RH strip, gives a general idea. You can use it to be a bit more specific. So for example, the National Trust have, I think they're called color meters or color, yeah, something like that. And they can find the precise fading to a scientific number of how much that is faded, but on the most part they use just to compare and see how much fading has happened. And we've got the electronic systems as well. So here on the left again is the LSEC. So this type of data logger, it does RH, relative humidity and temperature, and light and UV. So you can see here taking a reading of natural light. And again, that's a spot check. So you can check the levels, the current levels for a vulnerable object, and adjust the light as necessary. Or on the right, you can have a data logger or a telemetric light meter that does continuous monitoring, and then you can start to work out annual exposures. You can give a rough estimate of annual exposures using spot checks. by just taking regular spot checks and doing timesing it by the number of days you think it's exposed. But a continuous monitoring system, as before, will give a more accurate and reliable estimate of, not estimate, figure of what your annual exposure is. So with all these systems, they're great. However, they only work if you maintain them and use them correctly. So for example, that's all very well having your data loggers in and your continuous monitoring data loggers and telemetric Wi-Fi systems, but if you don't regularly download the data or look at the data, there is no point collecting it, because it still needs the human input to understand and react to it. It is not a system that most systems need human input. You need to look at the data, you need to be asking questions about the data and reacting to it. And just in general maintenance terms, all of the electronic devices need batteries or charging. If you don't do that, they stop recording. And one of the important things that generally gets forgotten is the fact that they do need regularly calibrating or checking that they are giving accurate readings, because like any other scientific instrument, it can become less effective or less accurate over time. So they do need regularly checking or sense checking to see whether they are giving accurate readings. And if they are not, they need calibrating. And annoyingly, a lot of the monitors I've mentioned can only be calibrated by sending back to the manufacturer, which is very annoying because it has a cost implication. But there are some that can be calibrated at home. But if you know how to check your sensors, you know when you need to send them back for calibration. I'm not going to cover that here, but it's important to be aware that you do need to check them regularly. Not like every day, but once a year. So we've covered what deterioration might be caused and monitoring temperature and relative humidity. So on to controlling now. So you've got your data. There are some things that need to be changed. You might, if you've gone outside of the recommended parameters, or you have a particular collection that needs a specific environment, how do you then change your environment and control it to achieve the environment you want? So there are a number of ways, and sometimes it might need one or two of them, or them working together in order to get the effect that you want. So very generally, in this country, our environment does tend to err towards the damp. So in general, a lot of museums, historic houses, need to control their RH to bring it down, to reduce it. We get a lot of rain in this country, and that means our RH is very damp naturally. Not all the time, obviously. It's when it gets quite hot, it can get quite dry. And in winter as well, if we have a dry winter, that's when we experience some dry, low RH levels. But in general, because of the amount of rain we tend to get, we very much generally need to reduce RH levels. So that's what I'm going to focus on. And you can do this a number of ways. because I explained the intrinsic link between temperature and relative humidity, if you raise the temperature, you will lower the relative humidity, because higher temperatures can contain more water vapor than low temperatures. So you've got a room at a set temperature that has a certain percentage of water vapor in the air. If you then increase the temperature without increasing the amount of water vapor that's in that room, you will lower the RH, because as a percentage, higher temperatures can contain a greater amount of water. So that same set level that you have is a lower percentage than it was in a lower temperature. Bit of a tricky thing to get your head around, but in general, if you raise the temperature, the RH goes down. And that is what is instigating this first control method. So conservation heating. Obviously, we have a lot of heating in our houses, in offices, in any human habitated spaces, and we have thermometers and thermostats that control heating, because when it's cold we want it warmer, if it's hot we don't want it on. However, in a conservation context in museums, we want the relative humidity level to control the heating, so that if it's very damp, we want the heating to come on to lower the RH, and when it's very dry, we don't want the heating on. And that can be a bit counterintuitive. So sometimes it's a very hot day, but it's very damp. So the heating's on to lower the RH. And sometimes it's very, very cold, but it's very dry. So like a crisp winter's morning, the heating won't come on because it's a dry RH. So it won't come on if it's humidistatically controlled, so controlled by the relative humidity. So here we can see a conservation heating system, a freestanding radiator that's controlled by a humidistat. And you can see on the humidistat, the light for power is on and the light for dehumidification is on, which means that the RH is such, it's above a certain level and it's turned the heating on to reduce the RH. It doesn't always work, because like I said, sometimes you can have hot days where it's very humid, and in that case, yes, ideally you want more heating to reduce the RH, but for comfort and for safety as well, because we don't want very, very high temperatures in museums, the heating won't come on. So at that point, that control is no longer effective. So you might need other forms of control. But in general, in this country, we tend to have lower temperatures and damp environments. That means that conservation heating can work quite well the majority of the time. So what do we do in cases where, not just in cases where we have high temperatures, but where you don't necessarily want conservation heating? You can introduce dehumidification. So dehumidifiers that reduce the relative humidity. If you've ever had a leak in your house or a flood, your insurers bring in these massive things that they turn on, whir, and try and get the moisture out of your house to dry it out, and they're dehumidifiers, and that's what we use in a museum context. So this one's quite a small one, controlling quite a small room, and again these can be controlled by a humidistat. So when the RH is high, the dehumidifier will click on and start extracting water vapor from the environment. The issue with dehumidifiers is that if they're quite small, they struggle to effectively control large rooms. So they only should really be used in quite enclosed spaces, not like tiny cupboards or anything, but normal size rooms. You might need one or two of them. The plus side is that they use less energy to run than heating control, because obviously and any of these electronic systems is always the energy consumption if you're having to use them all the time, especially in this day and age of high energy costs and increased sustainability. We don't necessarily want to be running very high energy systems. So which is why humidistat control is good, so that it switches off when it's not needed as well. The other thing about dehumidifiers is that unless they're plumbed in, they need to be emptied regularly. Otherwise they'll switch off, and they won't function and won't be controlling the environment anymore. So if no one's regularly checking and emptying your dehumidifier, there's no point it being there. But luckily for us, the one in the picture, which is on top of a massive shelf, is plumbed in, so no one has to climb up there to empty it. So if you can plumb them in, it is worth it, because it takes less maintenance, less manpower to maintain. So that's two systems, similar. Again, they're both controlling high RH environments. So not so much used in this country because, as I said, we tend to have a damp climate, but you can introduce humidification if you have a very dry environment that's going down below 40% quite regularly and you're worried about your collection. Humidification can be brought in, which it does the exact opposite of a dehumidifier. It puts water vapor into the environment. The only place that I've really seen these used is that, for example, in a historic house that's still used as a private residence. Because there's people living in the house, the heating tends to be on much more often, which tends to make drier environments inside. And in that case, they've put in humidification so that the collections aren't affected by the need for comfort heating. But that's only really needed in some certain circumstances, but worth considering. It is available if you do need it. And again, it can be controlled by a humidistat and would need plumbing in or filling with water regularly. So I'm not going to go into too much detail about HVAC systems or air conditioning systems. Obviously, a lot of modern buildings probably have air conditioning HVAC systems. They tend to be large scale, expensive systems to install, maintain and operate. So it's not an option open to all museums. And actually, in this sort of day and age, energy cost, sustainability, they're not ideal. However, they can effectively control environments. The only thing to make sure is these were generally installed for human comfort. So again, it's seeing whether you can adapt the system for collections, so that it's more controlled by humidity levels rather than temperature levels. Another drawback is the fact that they are bringing air in from outside. So if you're in a particularly polluting area next to traffic or roundabouts, things like that, they will bring in chemicals that can affect the collection. So they do need proper filters that are chemical filters that prevent that from happening, that need maintaining and replacing regularly. But that's all I'm going to say about air conditioning. They exist, they do work, but not always an option for many. And what I think is really the sort of more interesting aspect is the microclimates that I mentioned before. We've been talking, well, not necessarily microclimates, but we've been talking about electronic systems, but they're also passive systems. So things like artificial buffers that can help to control conditions. So for on a large scale, put a picture of a box here, but not necessarily on a small scale. On a large scale, it means making sure your building envelope is maintained, gutters are regularly cleaned, your roof is sound, There's no vegetation on the foundations of your building. Issues such as damp and things like that are rectified. Whether doors are fitting soundly, preventing air from coming in. So yeah, making sure you've got draft excluders, things like that. So little things like that can help to control the environment inside the building. On a smaller scale, for vulnerable objects that particularly are affected by RH and temperature, you can display them in display cases. You can store them in boxes. Display cases and boxes themselves will buffer the environment. So what I mean by that is, so if you've got quite a fluctuating environment, one with the RH and temperature that's going up and down, because you've put some material inside a box, a display case to all intents and purposes is a kind of box, it will reduce them fluctuations to a certain extent, because there's material around your object that has to acclimatise before the environment reaches your object. So even by the sheer action of putting your object in a box, that will buffer it from any extreme conditions that are outside the box. So on a larger scale, you can think of your museum as the first box, then anything else as a second box, individual rooms as another box, and then boxes and display cases as the sort of small scale boxes. If that helps you think, might not. But in addition to that, you can have artificial buffers such as silica gel, ProSorb, ArtSorb, and these are materials that absorb moisture. So they can be conditioned to a certain range. So for example, you can condition silica gel to maintain a low RH environment, which means it will continue to absorb moisture in that environment until a certain range, which will help to buffer display cases and boxes more suitably. For example, I've shown this box here of archaeological metals. I mentioned that archaeological metals need a low RH environment to prevent corrosion from occurring. And if you put it in a tightly sealed airtight box with silica gel, low RH conditioned silica gel, it will maintain them conditions on a quite affordable, low energy scale. In another way, you can also introduce dehumidifiers directly into cases or rooms to do that as well. But on a smaller scale, you can do that into boxes. And Amy's question was whether you can do that for other materials as well. And I think I've sort of answered that in the fact that any material you put in a box will buffer from extreme conditions anyway. Archaeological, yeah, so yes is the answer. The only thing to be careful with is that because we're putting things in boxes, we are reducing the airflow, so it will buffer the objects. However, if they are in a very bad environment, very damp environment, then it can also be damaging as well, because by sealing an object in a box, you're reducing the airflow. And if it's a damp environment as well, you might increase the risk of mold. So ideally, your outside environment would not be too humid before you box collections. But if you have a mid-range environment that's fluctuating, it will certainly help to reduce them fluctuations for any material. Yes, but just be aware that it can encourage molds, so you would want to check on the box collection, do spot checks to see whether there is any mold, any pest activity, because it's easy to think that things are sorted and nicely packed in boxes, but they're also kind of forgotten about. So we don't want to forget about things. We want to check on them where possible. It doesn't have to be every object regularly, just spot checks like and spot checks on random objects regularly, and it should highlight any issues. So there are also other types of microclimates as well, not just low RH. Freezers can be used for storing photographs, certain photographs, certain plastics in low temperature conditions, because as I said, materials with inherent deterioration mechanisms benefit from low temperature to reduce the speed of them deterioration mechanisms. Okay, so I think I've done a sort of basic intro there. If there's any specific questions from your museum about your environments and controlling, then please do put them in the chat and we'll come to them in a minute. So controlling light. So I've said we want to eliminate UV. So we want to do that. We can do that by using UV film on windows, because UV is in daylight, using laminated glass, UV absorbing acrylic polycarbonate sheet, or UV absorbing varnish for windows, skylights and display cases. And there are lots of different materials that absorb UV that can be used in a museum context. So actually reducing UV is not as difficult as it used to be, especially as we now use LEDs a lot, which don't emit UVs. If you do have older lights that are maybe tungsten or halogen, then there are filters available for them, which should reduce your UV to negligible. So that's easy. That can be done. Visible light, as I said, not visible light is more difficult because we need light to see by. However, in general, it's much easier to control artificial light than daylight. So where possible or acceptable, if possible, you can block natural light with blinds, shutters, things like that, and use artificial light. So, for example, low wattage lights, fewer number of lights, and diffusing the light by reflecting light rather than directing lights straight at objects. And also for very vulnerable objects, you might want to consider covering them for certain times, or making the visitor engage with the object by opening drawers or lifting flaps so that collections are protected from light, unless they're being looked at. And also potentially rotating displays. So for example, these flags, obviously one gets the brunt of the light and the one behind is protected by that one. So you can have a sacrificial object if you've got more than one object, keep one in the stores, one on display, or you can rotate objects on display so that they get a portion of the light light exposure. So that's sort of an overview of the main systems used to control RHT and light. But again, as with main monitoring, it really needs maintenance to ensure that the control happens effectively. So you need to keep all these systems in working order, particularly for electronic things. You need them to be serviced, pat tested, etc., to keep working. As I said, you need to empty dehumidifiers. You also need to replace and refresh exhausted materials. So, for example, I said the artificial buffers, such as silica gel, they do exhaust themselves, so you need to replace them and refresh them, so you can recondition silica gel and things like that, but you have to do it regularly. And that's where the monitoring comes in for them materials. You need to know when to do that. And you also need to monitor the effectiveness and adapt the control measures you've put in place. Don't just assume it's fixed, because it might not react as you've predicted. It's always a bit of a you have to see what happens. The environment is not quite as predictable as we'd like to think. Right, very quickly then, don't know how popular this will be, but we'll have a bit of an interactive session just to finish you off to wake you up in time for lunch. This might be very old hat for lots of you if you do take your own RHT readings, but I thought it might just be interesting to get you thinking about what might cause the data to look the way it does. So my top tips for reading RHT graphs are for your own museum is, first of all, have a look, are they within the recommended levels that you're trying to control within your museum? So I've just summarized them there again for a general collection. Where are the peaks and troughs, times of low and high RH and temperature? What factors may be causing this? So is it external conditions? Was it very damp on that day? Was it raining? Was it very hot? Is there any heating in the building or dehumidification? Were you open to the public that day? Was there a vent on? Could that be affecting the conditions? And also, what control measures might positively influence that environment? So if you've noticed that the external conditions are affecting the environment, is there anything you can do to control that? Can you introduce heating dehumidification to level out them peaks and troughs? Can you reduce comfort heating, which sometimes is the cause of quite variable RH conditions? And do you need any microclimates for vulnerable collections? So